Today we'll look at how to use the Design Space Explorer with SimCenter 3D. Here we have a parametric model of a bracket, and we'll begin by assigning a material property to it of steel. And because we'd like to optimize on two different materials, we'll also load aluminum. Next, we'll create a parameter that will represent the weight of our bracket by using the measure command and then creating an associative expression from it. And here we can see that weight. Let's go ahead and rename it so we'll be able to more easily identify it later. Alright, next we'll create our simulation models. And we also want to optimize not only on our linear static performance, but also modal performance. And to make the simulations run a little bit more efficiently, I'm going to turn off the solution monitor and hide our solver window for the solutions. Next, we'll create our modal solution. And we'll do the same here, turning off the solver monitor and the command window. Alright, we'd like to represent this model with shells, so we'll create a mid-surface representation of it. And then we'll bring that into the FEM, where we can shell mesh it. Now I have customer defaults set such that it will automatically inherit the material from the CAD model onto the shell properties. And not only that, but also we're inheriting the thickness data from the mid-surface. So here, if we were to plot the thickness contours, you can see that the model has 6 millimeter thickness, which was inherited from our CAD model. Alright, so next we're going to create some constraints, but we want those constraints to go into both of our solutions. So to do that, I'm going to create a folder, and we'll call it both, and you'll see it goes into the active solution but not the inactive one, so I'll drag it into our inactive solution. And then if we create a constraint within that folder, what you'll see is that that constraint goes into both solutions because the folder is in both solutions. Alright, next we'll put a load in our linear static solution that will press down on the bracket. And now we're ready to solve. And I'd like to solve all the solutions. We'll solve them sequentially. Here we can see that both solutions were solved. And let's take a look at our modal results first. Here we can see our first mode is at 592 Hertz. We can see what that mode looks like. And we can also take a look at our linear static results. And we're interested in optimizing on the Y displacement as well as our first mode frequency. So to begin, we'll create a result measure that will recover the Y displacement so we can use it in the Design Space Explorer. Next, we'll make our modal solution active so that we can create a probe to recover the first mode frequency. Here we'll give the probe a name and reference a canned result variable of frequency. And here you can see our first mode frequency is recovered by that probe. Alright, so now we're ready to go to the Design Space Explorer and create a new study, and we'll use the simulation workflow. Here we'll select both of our solutions by holding down the Control key. And then we can define our design variables. Here we'll select design variables from our CAD model, and here we have a number of named expressions that control the size of our bracket. And here for our thickness, we'll allow it to vary continuously between 5 millimeters and 10 millimeters using a 1 millimeter increment. We'll also allow it to vary the height to support continuously from 10 millimeters to 40 millimeters with a 1 millimeter increment. And also our section width from 11 to 20 millimeters. All right, now we also want to allow it to select what material would be best. So here we're going to create a discrete design variable to allow it to select the two materials that exist in our CAD model. Next, we'll create our design constraints, which will define our performance objectives for displacement and modal frequency. Last, we'll define a design objective which will minimize our weight. And there we can see our measurement expression that we created earlier as well for our weight. Let's go ahead and save, and now we can run, and we can select a random seed, and the default number of iterations will be 10 times the number of design variables that we have. So in this case we've got 4, so that's going to be 40 iterations. And here I'll let the solution run live for the first few iterations, but it's solving both solutions for each set of design variables that it's selecting. And after running the two solutions, you can see that it modifies the design and updates the mesh and then runs the solution again. So it will run through 40 of these iterations, and here I'll go ahead and pause the video after the next design change, and we can look at the results. So it's gone through all 40. And here we can look at our results, and it will list all of the various design iterations that it went through and categorize them as infeasible, meaning that it didn't meet our design constraints, or feasible, that it did, and then also it'll show us the best. And we can sort by our design objectives, so we can see that the minimum weight that is feasible is our best design. You can see all the steel designs are down towards the bottom as they're heavier, and the aluminum ones are up top. And we can go ahead and apply our best design, and it will go ahead and solve for those parameters, and we can see what that design looks like. So here we can see that combination of parameters. And there was one other thing within the results here. We have a summary as well that shows how many infeasible and feasible designs we have recovered. And then we can also graph the various parameters. So here we can see a history of how the thickness was varied as a function of the design ID, or height to support. You can also see the design constraints. And you can plot multiple ones as well, but in some cases it's a little bit difficult to read because of the scale. So if you do want to plot multiple ones, what we can do is instead show the 2D relation between a parameter such as the thickness and the height to support. It may make more sense to look at that thickness as it relates to weight, so as the thickness is going up, in general, the weight is going up. And if you need more parameters to see how they relate, you can create a 3D relation where we can look at thickness on the x-axis, section width on the y-axis, and see how all of that affects the weight. The Design Space Explorer helps you to quickly and easily optimize your designs.